I need to start this lecture out with a little bit of an explanation. This was recorded previously, and at the beginning of the lecture, we had gone back and reviewed some of the problems from the prior midterm exam. And I left in this recording those discussions for your benefit. And then we're going to pick back up where we left off at on Module 5, going into Lecture 2. As soon as we're done with that, it should be obvious when we get back to the Module 5 material. Thanks. This is the most important equation of this whole class. E, now it might have a different subscript depending on which machine that we're talking about, which type of equipment we're talking about. So I'm just going to say E. And what I mean by that is this is E. It corresponds to E1 if it's seen from the primary side, or E2 on the secondary. This is where you make the connection between the electrical and the magnetic world. And it's through Faraday's law. And this is where I think too many people miss this. Okay? If you don't understand this, go back and review it, because you're going to see it again. We derived an expression for these voltages for an AC system. It's going to have, in phasor notation, you're going to have an RMS voltage, and you're going to have some angle, which ends up being, as you'll learn today, if it's a machine, it's del. But really, it's the magnitude that I want to talk about here. So the magnitude comes, so where does it come from, right? E, here's the scalar version of it, is the derivative of the flux linkage with respect to time. Or it could be if you have a rotational machine. This isn't related to this problem, but it's going to be related. It's related to what was in the lecture last Thursday. The spatial derivative of the flux linkage. So we were able to derive an expression for this voltage that relates to the flux density. And it's square root of 2 pi times the electrical frequency times the number of turns. So whatever number of turns that you happen to have. Now, so we gave you the turns here, 75, times the flux density of the core times the area of the core. I think that's it. I did this, from memory here. So that equation is what you use here. So is there any questions about that? You're going to see this, that essentially why this isn't so important is that it connects the voltage to the flux density. The flux density connects you to the material that you're using. And it reflects the level of saturation of the machine. Okay, the magnetizing reactance too. I think most everybody got this, but it's just a matter of understanding, you've got enough information to do this problem there. This is the thing you got to know. So there were two things I gave you. The area of the core and the magnetic length of the path. And The other thing I did, which was just a little bit different, but I really tried to, I didn't give you a BH curve, but I try to treat our homework exams like a practical engineering problem. And sometimes your practical engineering problems don't look exactly like a homework problem. But if you think about what you learned, B equals mu H. So the mu was the only thing you needed to know that you didn't have for the reluctance, which you've got. It's 0.006. So, reluctance is equal to the length of the core over the area of the core over the reluctance. So it's actually a very, very simple problem. And I think people who had trouble with this really overthought it. I was pretty generous. Also because I think some people were throwing every single formula they could think of at some of these problems. And it's really trying to capture, what are the fundamental things we're learning. The next one is this. Now this is the thing. I gave you these values in per unit. And if there were some people who solved this without converting to the ohmic values, that was the first problem here. And that's a bit understandable because I think some people think, oh, well, this per unit's it's not the main thing. But it is a very, very important piece of this class. So I took 10 points off for not doing this. So the process is, if you're given the ratings and you're given per unit values, the first thing you need to do is find the ohmic values. So, we know the S base would be the 5 kVA that was given. I said that this was using the primary side ratings. So we would use V1 as the base. That would be 230. Then you can find an I base. This is a single phase transformer, so it's simply S base over V base. And then you need to find the Z base. I mean, you could combine these two into one step if you wanted. Some people attempted to do that. So the Z base, though, is V base over I base. And then you have to multiply, for example, R1 ohmic is going to be this per unit times Z base. And I stated that these were per unit impedances. Okay, now the other thing is this. I spend three lectures on Appendix A for a reason, okay? There were still people who did not know how to solve this using phasors. So I implore you to learn that and to not, lose any more time on that. It's not going to go away. So, essentially, to find the input current, you had to find the input impedance. It's a matter of practicing and try to give you enough homework problems to practice that skill of solving. So essentially, one of the things that might have thrown a few people off here, which I did things a little bit differently, is you would have had to know Z base. So does anybody know how you would find Z base? I mean, not Z base. This thing's a bad notation. This is Z load. I'm sorry. And that B is stupid. Okay, but doesn't, we should be able to get beyond that, those small details. But this load impedance. Does anybody know how you would find that load impedance? Someone's got to know. Yep. Okay, well, someone popped up and said it. That is true. If you know V2 and you know I2, the Z is going to be, now it may be on the primary side, the secondary side. So if you knew I2, these are all phasors. And we gave you that because we said that the load, there's V2 right there, and there's I2. And there's the phase angle. So we defined the power factor looking into the load. So that defines the angle of current. So it's essentially, 46. That means this is 0 because we defined it right at that point. Divided by the current, which is 90. It's lagging, so there's a negative inverse cosine of 0.8. And that's the Z. Then you just move it over to the other side and solve the problem. Okay? Now, I gave some people, and maybe it was a time issue, ignored this, and they actually were able to work the problem out quickly because they solved the current on the secondary side and transformed it to the primary side, and they got close to the right answer. So I gave those people a few more points, and I wrote a little comment like good insight, but that's not the right answer. But at least you're not giving me a completely bogus answer, because a lot of people, I don't know, I think it probably because they didn't account for this, but a lot of people had an input, like the input power factor, which I asked for, cosine of something that was very close to 90 degrees. That cannot be right, okay? There's no way, you don't have enough inductance in there to drive this thing to, and I don't even know if the sign was right. It'd have to be negative. It's going to be lagging if it's a transformer, unless you have a leading power factor load. So if you have a lagging power factor load, it's only going to get more lagging, but it's not going to go all the way to 90 degrees. So, I think I had a lot of people came up with this. I'm not really sure what happened there, but that's way, way off. And anyway, so I'm going to go move on from here if there aren't any other questions. But does anybody have any questions or concerns?
So what I understood from you is if we are given a load, it's better to work backward and get the current that is at the load, ideally, then make this reflect on the other side of the circuit. Because I'm the person who categorized, who got the very close to 90, the power factor.
Well, you weren't the only one. There were a lot
I'm
of people.
one of them. One of them.
Yeah,
Yeah.
right.
Yeah.
What did you do?
I worked from the primary because we used to always solve from the primary, not from the secondary.
Well, okay, so we've done it both ways. If you go back and you look at your homework, if you're given load information, it's like I say, if you're given the load information, work from the load to the input. And usually, and you're going to see the three-phase problems, especially in the next exam, we're going to have this. Most of the three-phase problems, you work from the load back to the source. So I give you what's the load, find what's the feeder voltage and current, right? And if you look, if you have not watched that extra lecture that I posted on three-phase, please watch it because I go through this and I actually give you an example of one where you would work it from the source to the load. And that's less common with most transformer problems. Because usually you're not given the load impedance. You're given the load current or voltage. So then you would work from the load back. So does that kind of clear it up a little bit? How to approach this problem? Mustafa?
Yeah, sure. Thank you.
Okay, yeah. Okay, we come up with the base key things that connect the synchronous machine magnetic circuit to the electrical circuit connection. So here is that equation. I said the most important equation of this class. There it is for a synchronous machine. Comes from Faraday's law. This, if you don't have this equation on your notes when you do your test, you will more than likely get some things wrong. And this is the equation I said that I still have it on a sticky note above my desk because I used to design generators, and I hadn't taken a class like this, when I got even from my master's degree. I learned, I used this over and over and over again. Now, what we do in the prior lecture is we derive this, we help you understand what this little factor is here, and it has to do with the distribution of the windings, because you essentially have an MMF that gets distributed around the rotational direction of the machine. So kind of like what I'm highlighting right here. And we go through that in this prior lecture. The other thing we do is we derive this. This is the flux per pole. So essentially what it is, and I'm going to go show you this from the lecture notes. So I've got these lecture notes. I used to give you a handout, which is a clean version of this, and I'm going to post these lecture notes right after class, which is marks up to track with the lecture. So what I mean by this is you have in a synchronous machine, you have a rotating magnet that is on the rotor, moving part of this machine. That thing that I just highlighted there, it's an electromagnet that's rotating. This is a 4-pole. We also go through the concept of poles, which is extremely important, and pole pairs, and so you really need to watch this lecture. And we can find it's essentially the flux that is crossing the gap here. I don't want to mess these up too badly, but you have a flux that's crossing the gap. Well, I think that's... I apologize. This is a 2-pole machine. I had made a point. I don't know why I circled it this way. This is a 2-pole machine. So you got the windings going in one direction over half of the circle and coming out. So it's going in and coming out. And so as a result, there's a flux crossing the gap. And the gap for this, it's called a round rotor or a non-salient synchronous machine, which is what we're pretty much focusing on in this class, is going to be constant. So there's a flux that's constant, and we call it flux per pole, the flux under there. So we derive that in this lecture. And the equations associated with the flux per pole, notice the little boxes around everything that's important here. So those equations, this one here, these two in particular, are derived, and they connect you back to the structure of the machine. Okay, so then we pick up here, and we talk also about the fact that you now have a flux, and the flux on the rotor has a rotational dependency because the rotor is moving. And so that means that there is a change of angle. So think about this as the rotor angle. If you take the derivative of that, if it's changing with time, that's the speed of the rotor. And we also introduced the fact that the speed of the rotor is equal to what we call the synchronous speed of the flux in the air gap. And that is saying that there's a flux that's moving as in synchronism, exact synchronism with the speed of the rotor that's connected to that electromagnet. And because of that, we then have a flux linkage that is time dependent. And if we take the derivative of that, now the flux linkage, and this I'm not going to go into too detail, it's in a prior lecture, but what is it linking to? It's linking to one of the phase windings on the stator. And so the synchronous machine has windings. Try to show you where that's on here. Right here. See, there's now windings on the not moving part, the stationary part. Notice all those empty slots, but there's these 1/3 of the slots are full. That's because we're going to have a three-phase machine here. And so we're looking at just one of the phases, and we're able to derive what we call a winding function, which because it's stationary, comes out to result in an effective or equivalent turns. It's the product of this little kW and the turns per phase. And so as a result, what you have is you have potentially three. This is kind of just showing undistributed, and we talk about distributed versus concentrated windings in the prior lecture, of three phases. You've got your A phase, you've got your B phase, and you've got your C phase. And as a result, you've got flux linking the field, rotating field, to the A phase, flux linking the rotating field to the B phase, and flux linking the rotating field to the C phase. And then if you take the derivative of those, which is Faraday's law, each one of those derivatives, the d lambda dt for each phase will have, because it's a balanced machine, balanced winding, will have the same amplitude. Next time I'll show you, but there's a bunch of animations on canvas that describe what's going on here, and it really helps you understand things. So if you go into the supplementary part of the canvas, right under the main page, There's supplementary materials. The very first item is a link to animations related to rotating machines. And we're going to be showing these quite a bit as we go forward. But if you want to start looking at those, I was going to show you one of the animations. But go ahead and look at that after class if you're interested. So we're going to talk about this completely from a mathematical standpoint, though, right now. So we also have a synchronous machine is a multi-winding machine. And there's actually 5 windings. Let's see, let me make sure I got that right. Why did I say 5? I think there's 4. Okay, so there's 4 windings. And as a result, each winding would have a flux linkage associated with that winding. So if we break this down, and I'm going to kind of zoom in here a little bit. This is the flux linkage associated with winding A. Winding A is on the stator. It has a flux linkage to the field winding, which is moving. And that's where we get this expression here. Okay, so that EAF RMS is derived from that flux linkage. And this is actually the open circuit voltage that you measure in the lab. And it would be the same from an RMS standpoint on every phase. We're showing this as a periodic scalar function. Notice that there's a B winding that also links to the field, and a C winding that links to the field. And if you go back up here, what I just highlighted again is associated with these flux linkages out here that I wrote as periodic scalar functions. So the first one here, the LAF, so you kind of have this scripted version of LAF. That actually has a position dependency in it. Some of these L's it's not a, it looks like this kind of a handwriting L. That's in the way they do it in the textbook. Some of them have rotor position dependencies and some of them don't. Well, in reality, it's just this one. If it's a round rotor machine, this is the only one that has a position dependency because the MMF is moving with position. Then the textbook talks about salient pole machines, but we won't go into those. But you've been introduced to that idea in chapter 3. If you have a round rotor, that means the gap is uniform, or the permeance as a function of theta r is not changing with theta, then these expressions here do not have any dependency on position. So if you look at what this is, because you've got 4 different windings, you've got a self-inductance for each winding. See the self-inductance terms? And those self-inductances multiplied times their respective current give you a self-flux linkage component. And then you've got mutual inductances to the other phases on the stator. Okay. So each flux linkage kind of breaks down this way. Does that make sense to everybody? Under no load, what do you think the flux linkage lambda A would be if you weren't loading this machine? What would it be? Anybody? Does anybody know? No? Seriously. At no load, what's happening? Where's my load? Can anybody answer that? When I say load, what do I mean? Are you guys at least hearing me? I haven't lost my sound. You guys hear me, right? Yep, okay, somebody said I can hear you. All right. All right. I think nobody wants to admit. Well, okay, the load is associated with what's on the stator. A, B, and C. So at no load, as it says right here, IA, IB, and IC are 0. And so as a result, at no load, these flux linkages would be 0. It's kind of like problem 1 on the exam where you're looking at you were just looking at a 2-winding machine and we were setting one of the currents to 0. And all we would be left with would be these mutual inductances and the self-inductance of the field if you were to no load. And that's what we look at when we're doing a no load test. And so at no load, we get this, which I'm really just kind of repeating what I've been talking about since the beginning of class. We get a time-dependent voltage on each phase of the machine, which could then also be expressed in terms of a phasor voltage. And this voltage is a function of the inductance, LAF, the frequency, and the field current. Now, because of symmetry of the windings, these are scalars. LAF equals LBF equals LCF. So the 3 windings are identical, the 3 phase windings on the stator, as far as number of turns, distribution factors, and then you've got linking that to a field winding. And so you would get the same voltage. Now this is another way of expressing, so this is actually a voltage, I could call it an E peak. And in the prior lecture, we derived a phasor representation which would give you the ERMS off of this. ERMS would be E peak divided by square root of 2, right? And so that would be omega E LAF IF over root 2. And now you have another way of finding the RMS voltage. If you don't have information about the geometry of the core and the flux density, but you do know what that inductance is, and you do know what the field current is, you can find the voltage. And so that's essentially equivalent to this expression right here. There's two ways to find it. One in terms of the flux per pole, which connects you to flux density and geometry, and it's also in terms of the turns, on the stator winding. Or you can write it in terms of an inductance here, a mutual inductance between the stator winding and the rotor field winding. So you've got these three things. Is that clear to everybody? Now, if you have a currents flowing in these windings, three-phase currents, then you would be using these full expressions right here. So these expressions are the same as these ones up here, but now what we're doing is we're substituting in the actual derived expressions for these inductances. And so these are just a number. These are the self and mutual inductances between the windings on the stator. And you have, in addition to that, a time-dependent flux linking you to the rotor. On the rotor, you have a field winding. What it follows is that if you were to combine the effects of these stator windings, this is really part of an armature. So we explained in the last lecture and in the lecture before that, if you kind of connect your machines up, going back to Lorentz force law, every machine really has a field and an armature winding. The DC machine, it's very straightforward because it has one armature winding that you can physically see and one field winding. In the DC machine, the field winding is on the stator and the armature winding is on the rotor. In the synchronous machine, it's inside out from that. In the synchronous machine, the armature is on the stator and the field is on the rotor. And all of these combine together to give you the full effect of an armature winding. So I kind of say an effective armature winding. It's the combined impact of all of these inductances and currents, or MMFs, that gives you that armature effect. So if we can actually simplify these expressions, recognizing because of the symmetry of the windings that all of the self-inductances are equal, all of the mutual inductances between the stator windings are equal, and all of the mutual inductances between stator windings and the rotor field winding are equal. If you do that, you can then come up with a simple you can write everything in terms of just two of these. So what we're going to do is we're just going to pick one of the windings. Just from convenience, we're going to pick the A winding. And so we have a self-inductance on the A winding, and we have a mutual inductance on the A winding, relating between the different stator self and mutual inductances. And the stator winding for phase A, which will be equal to it will be equal, as we say here, to the self winding of the B phase and the self inductance from the winding on the C phase. They're all equal. So we're only going to use this. So essentially what you're doing is you're substituting this in here. It consists of a inductance that really comes from the gap and the essentially the main flux path, which is really what we're saying. You've got a n squared, so you've got an n. I'll call it. Really, what it is you got a kW n times the phase. Let me clean that up here. You've got turns squared divided by some reluctance. And if you ignored the back iron contribution, or the iron of the rotor and the iron of the stator contribution, said that if mu is nearly infinite for everything that's in the core, this is just the air gap reluctance. It's that simple, okay? But then you also would have a leakage. So we talked about leakage when we were talking about transformers. You have a leakage associated with the flux that's not linking across the main flux path in the gap. If you also have a mutual inductance, but there is no leakage associated with that, and it's 1/2 of the self-inductance, and it's negative of the self-inductance. So you actually end up with a negative inductance, interestingly. So any questions so far? Well, if you plug all this stuff together, and if you assume that you're in the steady state, so we're assuming that we're in the steady state, we're assuming that we're balanced. That means that we've got the same current, the same load on every one of the three-phase windings. Then we're going to have these three currents. The current in the A phase would be IA times I peak. And I'm just assuming I'm going to select a cosine. I could use a sine. It's arbitrary. These are the scalar periodic representations of the currents. If I plug these currents, essentially plug this into lambda A, and you can also do lambda B and lambda C if you want, you end up with a lambda A. So we're just looking at this one right here, equal to this expression. So it actually simplifies down to a very, even though you have, so if you notice what you started with, you go back to I'm not going through all this math here because it would take the whole period to go through it. It's trig. You just do a bunch of trig. Unless you guys really want me to, I'll do it. But you can go off and do it yourselves too. But if you were to take these three currents here, plug them into this expression right here, and we're just saying, okay, I did that for phase A. That's what we just did. It will simplify down because of all these other things into this very, very simple expression here. Now what we have is, if you think about this expression, it has two pieces to it. It has this constant inductance, doesn't have any dependency on time, times the time-dependent current. So this IA is that IA right there. Notice that these other IB and IC are just different by 120 degrees. The trig will cause them all to just basically look like IA, and that's where you get this 3/2 factor here from the trig identities. And then you have, so this has a time dependency because of the current. And then this lambda AF is basically due to the rotating field. This is associated with the no-load voltage that you would have measured in a no-load test. And so we're going to define this expression right here is called the synchronous inductance. And it's a function of the self-inductance and the leakage. And now you can express all three of these windings in a very, very simple expression. Synchronous inductance times the current plus the mutual time-dependent flux linkage associated with the field. Now what we would do is we say, okay, if I have a lambda A, a lambda B, and lambda C, I can apply Faraday's law. So I'll just take the derivative of both sides. I've got d lambda A dt equals what is the derivative of the other side would be equal to, looking at this expression right here, the derivative of LS IA plus lambda AF omega ET. So taking the derivative there, now what is time dependent? Well, the current is the only time dependency here. That's the same as saying LS DI A dt. And then we'll just say d lambda AF dt, which we know what that is. And that's d lambda A. Now what you actually have is, and I want to try to draw a picture here for you. So is everybody with me so far? What we're getting to is, let's just say that I have a voltage VA of t, and I'm going to apply that voltage to my machine. So think about this, and there's some line, this is a cable. On the other end of this, there's going to be some inductance, and because it's in a winding, there is resistance. I don't have that, but there will be a resistance. So I'll call this RS. This inductance is LS. So essentially and then there's a voltage here. So this voltage right here is d lambda A dt. I just introduced one thing, and that's losses. Otherwise, it's identical to what I just showed right there. So I actually have a three-phase machine, though, because I have three windings. So if I were to say I've got a three-phase source on the other end, so this is VB of t, this is VC of t, got some cable going to that. This voltage right here is D. So talking about this voltage here for a moment, that's d lambda AF dt. We could also call it EAF of t. So there's LS and RS, because these windings are identical for the B phase. So here's A, B. This we could say is EBF of t. So there's a current going down here. This is IA of t. There's a current going here. That's IB of t. And then connecting it up to the third phase, there's a current coming in here, which is IC of t. So what I have is a three-phase, identical phases. They have a different current, and they have a different EMF. So this is your EMF, electromotive force, only different by a 120 degrees phase displacement. So it would follow that I could analyze, just like we did with the three-phase circuits, the transformer, I only need to analyze one phase of this and multiply my result by 3, and I can get my answer, if I can get this into phasor form. So is there any questions on this? Does that make sense? Usually somebody says at least yes. Okay, see one person said yes. Okay. What I just described up here, I said I've applied a voltage. What kind of a machine do you think this is? So in the last lecture, we defined machine. What is a machine when I say a machine? Does anybody know? If I say it's an electric machine.
It's either a motor or a generator.
Yeah, exactly. It's a motor or a generator. So what have I just drawn? Is this a motor or a generator? What do you think?
Motor.
It's a motor, right, because I'm applying a voltage to it. It's actually going to produce a torque. You can think of it as I've got a rotating shaft. This is kind of a lame picture here, but there's going to be some movement. You can kind of think of this whole thing as a round thing, and parts of it are moving and parts of it are stationary, connected to a shaft, and there's going to be some torque. I'll put a little sub E right there. It's an electrical torque. And you know what? The electrical torque, next time we'll talk a little bit about this, is going to be proportional to the sine of a torque angle. Proportional to the negative of the sine of a torque angle. So if I have a torque angle that's a negative angle, it's a motor. Now I put this as a del E. I might also call it just a del. But if del E less than 0, it's a motor. If del E greater than 0, it's a generator. Because it has to do with the torque. If it's a positive torque, it's going to be a motor. So these are the voltage equations that I have, and essentially this breaks out, right? The derivative of this breaks out into these two parts here. Now typically the resistance of a synchronous machine is very small. So it's common practice to neglect the RS because it's so small compared to the other voltages in the circuit. So in this case, the stator resistance is ignored. The armature resistance effectively gets ignored. So if we have, let's look at this one phase. And I'm going to look at the two pieces, right? So you've got LS di derivative of the current. And then I've got the field winding part, which is this here. What are the time domain periodic scalar functions? And actually, this is not exactly right. Plus some power factor angle. There we go. So I've got a power factor angle associated with the current. I think that was up here. See this angle right here? That's power factor angle. And then I have, interestingly, there's an angle associated with the voltage, and I'm going to call that del. And uncoincidentally, this is the same as the torque angle, or the power angle as it's called in a synchronous machine. And we talked about this, I can't remember, did I talk about this? Yeah, it's in the prior lecture. So go back and watch that. This is a bit of a review from the last lecture. But what you end up with if you convert these to phasors, this was a review right here from the last lecture. Here, this one that I'm highlighting green. If you take the derivative, if you basically convert that derivative to a phasor, you get this function, and then you get the other voltage drop across the reactance function here. And this now is omega E, it's the electrical frequency, times the synchronous inductance. Now in the last lecture, we introduced a relationship between the electrical frequency and what we call the synchronous frequency. It's the number of poles of the machine divided by 2, so that's pole pairs, times the synchronous speed. And the synchronous speed is the speed of the air gap flux. So there's a vector associated with that flux that's moving at that frequency. The synchronous speed in a synchronous machine is equal to the rotor speed. So you can also say omega E equals poles over 2 times the rotor speed. And then we can rearrange everything here, and now we have this, we've got this phasor representation of the EMF right here. So this can also be expressed as ERMS, and there's an angle del, and that angle is the power or torque angle. So because you've got this, we can now come up with an equivalent circuit in phasor form. So if we have a synchronous motor, then the current is flowing. The key thing to pay attention to is the direction of the current. So the current is flowing from the source to the machine. And this is your equivalent circuit that you can use to solve problems. And we end up with this. This is the voltage expression right here for a synchronous motor. If it's a synchronous generator, the current is going the other direction from the machine out to the source. Or you could say this is a grid. The electrical grid. Now what synchronous machines are usually used as the main generators that are supplying power to the electrical grid. So it's a good way to think about these machines just by assuming that there's kind of a fixed infinite bus that you're putting current into or out of. As far as this class goes, that's what we're going to do. I worked on my first job as an engineer was at Miller Electric, working on welders, and in the welder case we used synchronous generators for welders, and this out here, whatever that VA was, so just a little side point, if you had a welding generator, you would have had a JXS EAF. They would usually add another big inductor here to kind of smooth things out. I'll call it XW, welding inductor. And then this is the arc. It'd weld right off the generator. It's a resistor. So, and then the voltage, this would have been VA. But this is a very different case. It's if you had a little small three-phase standby generator, you might look at it this way too. If you had a single-phase generator feeding your house, kind of looks this way. Single-phase generators are a real weird animal. So we don't talk about single-phase machines. Believe it or not, if you go to Sam's Club and buy one of their synchronous machines, the mathematics behind that is really quite complicated. And there's very few people in the world who know how to design them today. You know, even if you go to the places like Generac and places like that, to really understand the physics of what's going on, drive it back into the machine, you'd probably be hard pressed to find an engineer who really understands it. I found that when I was at Miller, and you know, it's complicated. So that's it for today, and I'm going to go and give you an example problem next time, and then we're going to keep going, and we'll start. I'm going to show you some of these animations to try to emphasize what's going on here. Any questions? You guys are very quiet. I feel like this was a true lecture. Yeah, sadly. But it's hard to interact when we can't see each other, I know. So I can't tell if you're puzzled or not. For, you know,